Hello and welcome to today's lesson on the uses of radiation, which is part of the atomic structure topic in GCSE Combined Science Physics. So in today's lesson we're going to look at the uses of radiation in the real world. So if we've been successful and learnt in today's lesson, we should be able to state the basic properties of radioactive decay, look at the uses of radioactivity in the real world and explain how the different uses of radioactivity work, which falls into the following part of the GCSE Combined Science Physics specification: radioactive decay and nuclear radiation. In particular, the area that says students should be able to apply their knowledge to the use of radiation and evaluate the best sources of radiation to use in a given situation. Now, radioactive emissions can be used to carry out many different jobs in our modern world. So these include smoke alarms, thickness control, sterilisation, dating of materials, tracers, quality control and radiotherapy. So what we're going to do is we're going to recap how each use works and how they link into radioactivity. So the first thing we're going to look at is thickness control, which allows you to control how thick particular metals are made. So in thickness control, the amount of beta radiation passing through this metal foil depends on the thickness of the foil. Now, if the thickness of the foil increases too much, the reading on the detector would drop because more of the beta particles will be blocked by the foil. So the sensor adjusts the roller to make the material thinner so more radiation passes through. This keeps the thickness of the material constant, whilst conversely, if the thickness of the foil decreases too much, the detector reading increases because more of the beta radiation goes through the foil. So the sensor adjusts the roller to make the material thicker so less radiation passes through. This once again keeps the material thickness constant. So alpha particles cannot be used in this situation because alpha particles will be stopped regardless of the material thickness. And gamma radiation cannot be used as the level of radiation will be unaltered by the thickness of the material. Now this is for the thickness control of a metal. Now if we were doing the thickness control of paper, we would use alpha particles because alpha particles will be stopped if the paper was too thick, but will go straight through if the paper was too thin. Now another particular device which uses radioactive emissions is a smoke alarm. Now in smoke detectors, alpha radiation emitted by a source goes from one end of the alarm to the other end, and this causes a current to flow across the gap. This occurs because the alpha particles ionize the air particles in the gap of the alarm, so there's a current across the gap in the circuit of the alarm. So normally the alpha particles travel across, they then ionize air particles and complete the circuit, allowing the smoke alarm to work. But if smoke particles get inside the alarm, the alpha particles cannot travel across the alarm as the alpha particles are ionize the smoke particles, so it stops the current flowing and the alarm goes off. Now this effect can actually be also replicated by a deodorant can spray because deodorant particles will also do this. Now beta particles and gamma rays cannot be used in a smoke alarm as they would not ionize the air particles and they would not ionize the smoke particles. So it's important to know that beta and gamma emissions have a much lower ionizing power than alpha particles. Now alpha particles are safe to use in a smoke alarm as the alpha particles are kept far away from humans and they can only travel 5 centimeters in air. Now alpha particles are also safe to use in a smoke alarm as the alpha particles are easy to stop and would be stopped by the plastic casing of the smoke alarm. Now it's important to note you've got to use a source which emits alpha particles with a long half-life because it means the source does not need to be replaced very often. If you did not have a long half-life, it would mean the intensity of alpha particle emission would decrease very quickly and that in itself would set the alarm off. Now another use of radioactive emissions is quality control. So quality control is checking if a material has a crack in it. So to check a material for any crack, a film is placed on one side of the material and a source emitting beta particles is placed on the other side of the material. If there's no crack in the material, beta radiation is emitted from a source. It then gets stopped by the metal and doesn't show up on the film. If there's a crack, the beta particles go through the gap without being stopped and this shows up on the film. So if there's no cracks, the beta radiation is stopped by the metal and doesn't show up on the film on the other side. But if there is a crack, the beta particles go through the gap without being stopped and this shows up on the film, causing the film to darken. Now alpha particles couldn't be used in this situation as they'd be stopped by the air, and gamma radiation could not be used because they'd all pass through the materials and all show up on the film. Now, we also use radioactive emissions in sterilisation. Now, in sterilisation, gamma rays are fired at a source, and this kills off any microbes on the object by ionisation, which is an example of irradiation. Now, this prevents the object from causing an infection to a patient, and it's also used by supermarkets to keep food fresh for longer, because it's the microbes on the fruit and vegetables that make them go off. Now, the higher the dose of gamma radiation, the greater the amount of ionization. So it's important to know that the gamma radiation destroys the cells of the microbes, and it's the same process as radiotherapy. So in radiotherapy, it's cancer cells which are destroyed by the gamma radiation. Now, the half-life of a particular radioisotope can be very important. So for example, carbon-14 has a radioactive half-life of 5,730 years, and we use it in carbon dating to work out the age of various fossils. So when a living organism is alive, it takes in as much carbon as it releases due to the carbon cycle, which is what you cover in GCSE biology. So if we consider the carbon movement for a tree, it takes in carbon via photosynthesis and it releases carbon via respiration and decay. Now, some of the carbon moved will be the radioactive isotope carbon-14. Now, it's important to note that the radioactive carbon-14 has the same chemical properties as the non-radioactive carbon-12, since they've got the same number of outer electrons. So a tree, a plant, doesn't distinguish between the two of them. Now, carbon will still be released by an organism when it dies, but it will no longer take up any new carbon, okay, in this process. Now, so what we'll do is we'll assume that when a living organism dies, the amount of carbon in it stays fixed from that point of death. Now, in reality, that's not the case, but because you've got to think that some carbon would also be lost via decay, but that's quite a complicated calculation, which you cover at A level. Now, what happens is if we say the number of carbon atoms remains fixed in the organism, the number of radioactive carbon-14 isotopes will decay into more stable isotopes over time. So carbon-14 will decay into into nitrogen-15 by beta decay, and as it's producing a new element, we call that transmutation. Now, what we can do is we can compare how many radioactive isotopes remain in the dead organism and compare it to how many radioactive isotopes are found in the equivalent living organism. Now, remember, the living organism will have more radioactive carbon isotopes as it's still taking up carbon, including carbon-14, because it's still alive. So we calculate how many radioactive nuclei have decayed. We then know one half-life is 5,730 years, so we can therefore work out how long it's been since the organism died and stopped taking up carbon, which we call carbon dating. Now, for carbon dating to work, the substance must contain carbon, so it only works on organic matter. Now, igneous rocks don't actually contain any organic matter such as carbon, so we've got to use something else instead of carbon, so we use uranium. We measure how quickly uranium decays. Now, just a note, for carbon dating to work, the substance must still have some radioactive carbon isotopes in its structure to measure. So this means we can't use it on materials which died a very long time ago, as all of the carbon-14 nuclei will have decayed. But by that same process, for carbon dating to work, the substance must also have a different measurement to a living organism. This means it's very difficult to date organisms that have very recently died, since there's not a major difference in the levels of carbon-14 between the living and the dead organic matter. So, how do you work out how old an organism is via carbon dating? Well, you measure how much of the radioactive carbon isotope is in a living organism. You then measure how much of the radioactive carbon isotope is found in the equivalent dead organism. You determine how much radioactive carbon has decayed over time and become stable, assuming that no carbon gets lost out of the organism over time. We then use the half-life of the carbon radioisotope and work out how much time has elapsed for this amount of decay to take place, but we can only use this method if there's a measurable difference between the carbon radioisotope between the living and the dead organism, and we can't use this method if there's not been a long enough time for a noticeable difference to form between the two, and we can't obviously use this method if that's the case, because there's no actual difference to then work out how many half-life half-lives have been carried out. So we can use radioactive decay to measure the age of materials, and there's two processes to do this. Carbon dating, which is used to find the age of wood and organic matter. All organic matter contain a tiny amount of radioactive carbon, and this has a half-life of 5,700 years. So when an organism dies, it no longer absorbs carbon, so the amount of radioactive carbon decreases. So to find the age of matter, we measure the count rate of the dead matter and the count rate of the living matter and compare. We can use uranium dating to find the age of igneous rocks. These rocks contain radioactive uranium, which has a half-life of 4,500 years. Each uranium nuclei decays into lead, and we can work out the age of a sample by measuring the number of nuclei of uranium and lead and comparing the two. So what should we have learnt in today's lesson? We should know the knowledge of the properties of alpha particles, beta particles and gamma particles in terms of their penetration, range and ionizing power, and you should be able to apply this knowledge to the uses of radiation and evaluate the best sources of radiation in a given situation. So if we've been successful and learnt in today's lesson, we can state the basic properties of radioactive decay, we can look at the uses of radioactivity in the real world, and we can explain how the different uses of radioactivity work. So I hope you've enjoyed today's lesson on the uses of radiation, which is part of the atomic structure topic in GCSE Combined Science Physics. Thank you very much for listening and have a lovely day.